Hey guys, what's up? Eddie Ahu here with KissAnalog.com. Guys, today I want to go over a buck converter, kind of show you how a buck converter works real quickly, but I want to go into the two-phase buck converter and show you how that works and the benefits, okay? I'm going to bring you over to the bench, show you this GANFET, this eval card I got from Efficient Power Conversion, EPC. Has a analog device or LT control chip on it. It's really neat, and I've done a video where I've shown it before, but this time we're going to look to see, it's a two-phase buck converter. So I'm going to show you the benefits. And as a matter of fact, let's pull up the whiteboard. I happen to have a whiteboard handy. Here's a buck converter, okay? I made it big. We're going to end up pretending there's a second one down here. But this is a buck converter. See, it says buck. This FET, when he turns off, he doesn't let any input voltage come out to the output. If he's on all the time, the output's going to be equal to the input. That's a buck converter. You know the FET's failed if you're seeing the output voltage come out. As you bring the voltage up nice and slow, if the voltage coming up on the output, same time it's coming up on the input, that FET's shorted. There's a troubleshooting tip. When it starts to switch, when the power supply comes up, the way it should work is you won't see anything until this guy starts to operate. He should be open. When he starts to switch, he'll turn on. When he turns on, like any kind of switching power supply I can think of, whether it has a transformer or an inductor, there's a magnetic or inductive element. It works with the switching element. That's what makes switching power supplies for most power supplies, most switching power supplies. So this guy turns on, he charges up this inductor, starts sending current to the output, but he doesn't want to put 20 volts out here, so he turns off. And then he waits for a little bit, then he turns back on, and he tries to regulate this to 12 volts. Okay, that's the setup I'm going to do back here. So, but you know what? Imagine this is 24. I should have just done 24. If it's 24 and 12, then he'd be on half the time, off half the time. So half of 24, so yeah, this guy would average, between the inductor and the capacitor, it'd average that on-off time to get 12 volts out here. You know, minus some drops across the inductor and across the FET, right? But yeah, so duty cycle, how many times, if you got, say, 1 microsecond, how much of that 1 microsecond can be on? So you say, well, my output's 12 volts, my input's 24, 50%. Okay, so pretty simple. All right, so now this guy, what's he doing here? Well, when this guy turns off, current in the magnetic device doesn't want to stop instantaneously. So current's flowing this way. He turns off, he's going to pull current this way. And so this capacitor and diode is going to keep current flowing this way. So that way, the inductor is happy, he charges up and he discharges, okay? And then you're going to give another pulse, okay? And you're going to try to regulate this to 12 volts. All right, so there's your buck converter. Two-phase buck converter. Imagine two of these circuits working together. They both come up here and you tie the outputs together. There you go, two-phase. Well, that's not two-phase, that's just two parallel buck converters. So the phase part is you change the phase. When this guy's turning on, the buck converter down here, you turn him off. So that way, this guy's on, he's pulling current from the input, then he turns off, then the current from the input goes to this one. So the current from the input is kind of on a lot of the time. There might be times when it's off, depending on duty cycle, depending on this setup. But current's continuously being pulled, almost, right? And maybe in some conditions it will be pulled continuously. But you'll get half as much current to this one, half as much current to the second buck converter that's down here. And then they get parallel together to give you your full output current. So remember, voltage drops, because of current, say current through the resistive element of the inductor. There's a resistive element part of this, right? It's DC resistance of the inductor. This one has a resistive element that's the RDS on. It's the resistance between drain and source when it's on. When it's on, you got some resistance and there's some bulk resistance. So current, the voltage drop there and the voltage drop here is I squared R. So it's a squared function. So if you drop the current in half, you're dropping the dissipation quite a bit, right? So by dropping the power in half here and adding a second converter half here, these guys are operating a lot cooler, okay? Okay, back to this guy. What's he doing here? He's providing that flyback. Some people call it a freewheeling diode. So he's just hanging out. All of a sudden, this guy turns off, and this guy says, hey, I still need current. And he goes, oh, okay, I'll supply it. And so he freewheels. The nice thing about that is he just turns on when he's forced to. There's no gate, there's nothing, there's no timing element. He's just like, oh, I'm supposed to be on now. Okay, I'm forward bias, I'm on. We're going to replace him on this board. He's replaced with a FET. So we call that synchronous rectification instead of just passive rectification. Now it's synchronous. It's synchronous because there's a timing element. You have to turn this guy on, let him do its thing, turn him off, wait a moment, because there's a dead time plus a delay time for the current to ramp back up or stop ramping through here. So you got to wait for all those functions and then turn him on. So you have to synchronize that. So it's synchronous rectification. So now we have two buck converters working together. These parts, if you had, let's say this is 100 kilohertz and this guy was 100 kilohertz, if they were working in parallel without the phase, without changing the timing, if you just put the gates both together so they both turn on at the same time, they'd both be pulling current at the same time from the input, and then they'd both be off at the same time. So the current from the input is going to see this big current, then off. It'd be just like operating one. It wouldn't know there's two. Same with the output. So by putting him out of phase, turning him on, with him off, and then turning that guy off, and then turning the second one on, now you get half as much current through him, and then he stops, and half as much current through him. You get a continuous current flow. So now it's more continuous. There's not as much dead time out here, if any, depending on this relationship. So the current for EMI purposes and for storing, using capacitors and filters out here, storing that energy in between dead times or on times, it's almost on all the time. It's a lot easier. It's kind of like the freeway. If traffic just all goes the same speed all the time, just think how much better that is versus, a big old pile of cars that goes real fast and runs into the second pile, stops on the freeway, and you're like, and then you take off again and you stop, right? That's not good. Same thing with the output. You get half the current coming out here, and then that stops, and then half the current come from this one. So the output and the input looks a lot better. Okay, so let's come over to the bench. It'll be easy to see here, but I just want to show you the schematic. Now let's come over to the bench. Hey, by the way, give the video a thumbs up if you like this kind of video. And yeah, that'd be helpful. Okay, thanks, guys. All right, guys, this is a setup. These leads here are going up to my active load right there. So I'll be pulling current there, okay? And I've got a current probe we might look at. I've got the voltage probes set up here from my Uni-T multimeter over there. But I've got one scope probe looking at this channel. So from over here, let me move that guy. You can see, all right, they're very small, but here's a control chip, okay? There's two FETs here, there's two FETs there. Those teeny little black things are GaN FETs. One output inductor, another output inductor. Then here's an output, here's an output. So I've got this wire here, this probe here, tying the two together, okay? The center one's the return, okay? So here's my load right here. It's tied between those two. Now I could have, these two are tied together, right? So, all right, so let me put this back in here. So that is so these two probes are tied into the switching node of each converter. So we'll be able to see it, okay? So here's the input. These are those Hirschmann test leads. They're so awesome. And all right, guys, so here's the power supply over here. Maybe it'll focus on my hand. It's kind of funny how it'll stop doing that. Yeah, there it goes. Isn't that funny? I don't know. That's weird. But anyway, so I've got the set for 20 volts, 5 amps current limit, because we're going to pull some current. So I just have to hit the on-off button to turn on the power. But I want to come over here, show you the scope. Okay, the power supply is running now. Look how crazy that is. Let's see if I can get it triggered better. Sometimes it come up to a peak or something. It's just kind of nuts. And that's because there's the cycles or there's regulation going on. There's a lot of weird stuff here. Let me show you what I'm talking about. Wow, where'd it go? I just froze it, but where'd it go? So here, let me scrunch these things together. Look, there's a burst, a burst, a burst. So this is something I didn't mention. It's trying to regulate. It's like filling up that output capacitor with water. You get it so full, any more it's going to leak out. You're going to get too much voltage. So it turns off, and then it kind of drains. It leaks a little bit, and then it bursts and puts some more on there. So the burst time, the off time's longer than the burst times, right? So then when we zoom in, whoops. So let me move this over right in the middle of the crosshairs there. So when I zoom in, we'll be zooming in on a burst. Okay, so see, oh, look, remember I said it wiggle when it was turned off? It's going to sit there and wiggle, but each time it does, it wiggles a little bit. But when it really turns off, it just sits there and wiggles, okay? So let's check it out. Here, I'm going to move it over so that rising edge right there's on a crosshair, okay, just to make it easy. So across here, a FET's on. So the input voltage of 20 volts, it says 20 volts right here. The input voltage is putting 20 volts on that switching node. Charges up the inductor, current's going out, turns off, and then the diode turns on and pulls it down to just below zero. So we got that point, that diode drop. But it's really a synchronous FET. So we got a synchronous FET drop right there. So then it's off for a little bit, and then it turns back on. Now, duty cycle is about 60%. I mean, 20 volts in, 12 volts out, it'd be 20 volts if it's perfect. But, you know, might not be exactly 12, might be 12 point something. And also we have the dead times to consider too. All right, so there's that. So here, let's run it again. Okay, now I'm going to turn on the other channel. Okay, let's freeze it again so we can see what the heck's going on. Okay, I'm going to have to move this waveform over like this. Let me scooch it over, and then I'll zoom in. All right, so you can see transistors off. Okay, dial or the synchronous FET's doing its thing during this on this cyan color. Then the cyan goes up, it overshoots a little bit, and then it settles down, and we got 20 volts, and then it turns off, and then that synchronous FET pulls it back down. Okay. So that's the way that works. Now, meantime, the other converter in parallel is doing the same thing. It's on during this time, then it's off during this time. So there's always one on, it looks like, right? There's a little overlap where they're both on. They're both on. And that's just because of the ratio of the on to off. If I did have that 24 volts, here, you know what? Let's go ahead and just do it for fun. I'll put 24 volts on the input so we get more of a 50% duty cycle, right? Let's do it. Well, actually, first thing I want to do, you know what? So this burst thing's not driving us crazy. Let's bring up the current, and you'll see more activity happening. The burst, here, let me stop it again. We're going to zoom out. Look, now this is on, the burst is on longer than it's off. Okay, I'm going to leave it right there. And we'll see when I bring up current, you can kind of tell it's getting less and less. Pretty soon, they're both going to be on all the time. Yep, there we go. Look at that. All of a sudden, it straightens right out. Okay, I'll freeze that. Okay, now let me zoom in. Now you see it's continuous, right? There's no more burst. And check it out. So there's that overlap right here. Same thing, but now it's continuous all the time. So no more burst mode because you know, we need to keep charging that inductor. There's enough load that's taken off current off that output capacitor that it has to continually run. So you can see this part's the switching. This is switching noise up here. All right, pretty cool, huh? Now, you know what? I'm going to stay zoomed in like this. Here, let's turn off the power supply. Let's turn it back on. And I'm going to, okay, I'm at 20 volts, right? I'm going to bring it up. 21, 22. Okay, there's 24 volts. I'm going to go ahead and freeze that. Now look, the off time and the on time on the cyan, it's about 50-50. Same with the green one. Now look, there's very little overlap because they're both on and off 50% of the time. Pretty cool, right? So now imagine if I bring up the voltage even higher, then there's going to be dead time where neither one of them are on. Let's do that. Let's make a run. Whoops, got to turn on the power supply. Okay, I'm going to take it up a little bit higher. Okay, let's freeze that. Yeah, check it out. Now there's time when both of them are off, so both synchronous FETs are on, and there's dead. Then one turns on, then it's off. Oh, the other one turns on. So you can see that at this point, the current on the input is, the current of the input's almost been taken equally all the time. So the ripple current on the input is much better. Output, same thing, because we're supplying current all the time. So yeah, you can see, I hope that was a good show of the benefit of the two-phase buck converter. All right, guys, so what do you think? That's pretty cool, huh? So hopefully that was a good visual, give you a good understanding how not only a buck converter works, but a two-phase buck. You turn off either one of them, it'd work fine. Just wouldn't be able to get as much power out. Sharing the power between two works much better. EMI looks better on the input and output. I mean, it's just good all the way around. The other thing, it takes you more components. Now you have 4 FETs instead of just 2. You have 2 inductors, so more parts, but they're smaller, right? You can choose smaller inductors. You can choose smaller parts because you're not putting as much peak current through, say, the inductor. So the core isn't going to saturate as easy. The wire size can be smaller too. Everything can be smaller. So anyway, hope you guys like that. Like the video. Appreciate that. It helps the video, the channel a lot by sharing, liking the video, and subscribing. That'd be awesome. Hope you like this. We're going to do more things like this. I'm going to show you. That was a burst mode. I kind of brought that out. I just thought as I was running, I may as well show you that. There's a couple other modes of operation this has for light load. Light load is where things like, what are you going to do? You're going to keep on supplying power to the output when it's not taking any power? You can't do that, right? There has to be ways to handle that. The burst mode is one way to do that. So I'm going to talk more about that kind of stuff later in another video about how burst mode and those things affect EMI. But yeah, for now, what do you guys think? Two-phase, right? 2 big thumbs up to Danny, my YouTube member, or he's my team member. All my other YouTube members. Appreciate you guys. And my patrons. Yeah, appreciate all you guys that support the channel and help me buy like the Hirschmann Test Leads I bought. I bought it. Yeah. I didn't realize. Anyway, that's another story. But anyway, hope you guys liked the video. Thanks for watching. See you next. Oh, you can. Hey guys, you can become a Patreon or a YouTube member by just clicking the links down below. There's a super thank you down there. If you want to buy me a coffee or a beer for a rant, I'm due for a rant. I was going to do one and I put it off. So I'm going to have to soon. All right, guys. Thanks for watching. We'll see you next time.